Again.
Okay, good morning, everyone. Welcome to the last week of classes. Questions, how did the homework go? Do you guys have any questions whatsoever before we start? Okay, so today we will talk about what I started last time, the idea of diagonalization. I motivated it last time, but today we will actually work with it. So let us recall the definition. So we have a n by n matrix A. We say that A is diagonalizable if we can find two matrices. A diagonal matrix D, oh, sorry, Daniel, I didn't read it, 9 and 13 on 5.2. All right, I will do one of them because I think they are similar and I proceed to my lecture, okay? So, sorry, I will stop. I will go through your questions and then I'll come back to our lecture. So 9 or 13, let me look that up. 5.2. Okay. So I will pick number 13 and I will do that. Okay, so number 13. And we will do a lot of problems. We will be doing a lot of problems along those lines today also, because this section is basically an application to eigenvalues, eigenvalue problem. So I have the following matrix. It's a 6. It's -2 and a 5. And it's a -2, 9, 8. And it's a 0, 0, and a 3. So that's my matrix A. And the question is, find the characteristic polynomial. And then I asked you also to find the eigenvalues and find a basis for the eigenspace that correspond to them. All right, so we're going to do that. So the characteristic polynomial is nothing more. So the characteristic polynomial, this is nothing more than the determinant of A minus lambda r. So that's the definition of it. So we compute the determinant of A minus lambda r. And it means you take A, you take away from it lambda times the identity. Right? So we do that. So I will get 6 minus lambda, -2 and a 5, -2, 9 minus lambda. I'm just taking things away in 8, 0, 0, and a 3 minus lambda. And we have to compute this determinant. Now, of course, we studied cofactor expansion for a reason, so we can compute the determinant in an easy way. And as I said last time, most of the matrices I will give you, you can compute the determinant and solve for determinant equal to 0 in an easy way. Otherwise, this is a hard problem because a characteristic polynomial for a 3 by 3 matrix will be a polynomial, a cubic polynomial. It means it will be in lambda to the power 3, which is in general very, very hard to solve. But there are a lot of algorithms on MATLAB, you guys, the computer algebra system that you guys are familiar with that can solve those problems. But what I give you, what the book is giving you, are rather simple. So definitely I have to do cofactor down this column because that's the easiest one to deal with. And let us remember how we do it. I start with my checkerboard sign. Plus, minus, plus, minus, plus. So this would give me 3 minus lambda times the determinant obtained by removing the row and the column where 3 minus lambda is. So this would leave me with 6 minus lambda, minus 2, and 9 minus lambda. So now I have to compute this determinant, and that's a characteristic polynomial. So that's 3 minus lambda times the determinant of that. So that's 6 minus lambda, 9 minus lambda, minus minus a plus, and a minus, I will have minus 4. So this will be equal to 3 minus lambda times lambda square, minus 6 minus 9, minus 15 lambda. And here I will have 6 times 9, which is going to give me 54, 54 minus a 50. Okay, so that's the characteristic polynomial. It's just a polynomial. I will not distribute because my second question for you was, so that's the characteristic polynomial. Find the eigenvalues. The eigenvalues are what we call the roots of the characteristic polynomial. It means we have to set equal to 0 and solve. Okay, so this will give me equal to 0. I have to solve this polynomial. Now be very careful. Solving really is factoring. That's why I did not distribute this term. She should be plus 50. I appreciate any mistake I do because it's crucial. Thanks, Mark. Yeah, thanks, Matt. So, yeah, what I was saying. Yeah, do not distribute because solving is factoring. If you distribute, you're going to get lambda to the power 3 and you will have no idea how to solve it. So solving is really basically factoring. Now, this is already factored, so I have 1 lambda equal to 3, and now I will see if I can factor this one. If I cannot, I use a quadratic. If I cannot, we will, usually those are cooked, so you guys can do it. So this is the 50 equal to 0, 50 and 15. So this is going to give me 10 and 5, that's for sure. That's the 10 and the 5. And I have a lambda, and I should have a minus. So these are the eigenvalues. So we solve, we get lambda equal to 3, lambda equal to 10, lambda equal to 5. So I have 3 eigenvalues, which are distinct. They are different from each other. And these are the eigenvalues. So I repeat, when you solve it, do not distribute because you lose your solution. We just keep it. We try to factor. We do not try to do anything else. Now to find the eigenvalue, of course, I will not do all of them. I will just pick one. So suppose I want to find a basis for E3. It means I want to find all the eigenvector that correspond to lambda equal to 3. So find basis B3, it means I'm finding all the vector x, such that A times x is 3 times x. That's really what I'm finding all the eigenvectors. Every x, such that the matrix A is stretched by a factor of 3. But that's really equivalent to solve the following homogeneous system, which is way easier to solve. Okay, so I just look at this one. I will not do anyway. I will not go further than A3 because you will be doing a lot of problems along the same line today. So I will not repeat it several times. So A minus 3I. So I have to solve this system. So I have to plug 3 for lambda into the equation. So this is going to bring up the following. 0, 0, 0, and I have to back up to the original matrix right there, and I have to take minus 3. 6 minus 3, it's a 3, minus 2 is a 0, minus 2, 9 minus 3, it's a 6, and says 0. That's a 5, that's an 8, 3 minus 3, it is a 0. And now we have nothing left except solving. So please correct me if I'm doing any mistakes. So I have to solve. If I am solving it, I will move this row to the top divided by minus 2. Then this would give me 1, divide this by minus 2, divide this by minus 2, minus 3, 0. I will do it this way, so I simplify the process, and 5, 8, and 0. Now by doing this, I create a leading of 1 in here, which will make do this stuff by hand much easier. So I'm almost there. Minus 3, 0. Minus 3 plus 3 is a 0. That's where I will do mistakes. Minus 3 times minus 3, that's a 9. 9 minus 2, it's a 7. And then, what else do I have? Minus 5 plus 5, it's a 0. I have to multiply this by minus 5. That's going to give me a 15. Okay. This will give me a 15. 15 plus 8, 23. 0 and a 0. So this is a leading. This is a leading. This matrix is not in echelon 4. I will have to make it into an echelon 4. So to make it into an echelon form, I cannot stop. 1 minus 3, 0. I can make this into a 1 by dividing by 7. And then I multiply by minus 23. And I add. So I end up with this one. So we solve. X3 is 3. X2 will be 0. And X1 is 3. X2, it means it's equal to 0. So my eigenvectors will have the 4 T for X3, 0, 0, 1. So every vector that satisfies AX equal 3x, any vectors that satisfy AX equal 3x has the following format. So a basis for E3 is the vector 0, 0, 1. Okay, so I will not do all of them. For lambda equal to 10, we do exactly the same. Lambda equal to 5, we do exactly the same. All right, so that's how we handle the eigenvalue and eigenvector problem. Okay. Number 9 is along exactly the same line. That's why I will not actually do it, because as I said previously, we will do a lot of problems to deal with this question. All right. Okay, any other questions besides those two? Great. So now we're going to go back to, we will go back to the idea of diagonalization, and I review a little bit what I did last time. So A is diagonalizable if I can factor it out, basically. It means I can write it in this nice format. P has to be invertible because I'm talking about its inverse. P is, so suppose A is n by n. P is in n by n invertible matrix. And D is a diagonal matrix. It means D has a bunch of numbers here, and it is 0 everywhere else. So it is a diagonal matrix. That's what a diagonalizable. And then we saw a simple application. If A is diagonalizable, I can take A to any power, positive power. And it's very easy to compute the powers of A. That's what we saw last time. So if I can write it this way, I can take A to the 100. It's P times D to 100 times P inverse. And diagonal matrix are easy to take their power. So if A is diagonal, so like it has D1, let's say D is a 3 by 3 diagonal. Then raising it to any power really boils down to raising the term along the diagonal to the power. So multiplying a diagonal matrix by itself is rather a simple fact. So that's what we've talked about last time. Then before I stated the theorem, I motivated the following idea. I said, suppose A can be written like this. So the question is, what's the P? And what is the D? And last time I tried to a little bit give you an idea. So I wrote the following. Let's A be 2 by 2, just to make our life a bit easier. So if A is 2 by 2, all those will have 2 by 2. Suppose A is V1, V2. And D is the following. So suppose I can write A this way. What is? My question is, what's the P and what is the D? All right. By setting this up, I played a little bit with this equality by multiplying by P. I set it up this as AP equal PD. And I showed you the following, that if this holds, then AV1 should be equal to lambda 1 V1. So the columns of P should satisfy the following property. And AV2 is lambda 2 V2. That's what I tried to work with last time. So this means two things. It means that if V1 equal lambda 1 V1, it means V1 is absolutely have to be an eigenvector of A with corresponding eigenvalue lambda 1. Means this column of P has an eigenvector. And this one is the eigenvalue that corresponds to it. So if this decomposition hold, if this factorization hold, this is what V1 and lambda 1 is. V2 is another eigenvector. And lambda 2 is the eigenvalue that corresponds to it. So if everything works, that's exactly what the P should be, and that's what the D should be. Moreover, if this P has to be invertible, because that's what I want, if I want P is invertible, this tells me that V1 and V2, which are eigenvectors, should be what? If P is invertible, it means the columns of P has to be linearly independent. Otherwise, this P is not invertible. So that's going to will be the motivation of the theorem we will be about to say. So if I can write a matrix this way, then the P will have for columns the eigenvectors. The D will have for columns. Sorry about that. The D will have for diagonal the eigenvalues. So that's really what the picture would be. And if I want P to be invertible, the V1, V2 has to be linearly independent. And this will motivate the first theorem that you will work with. So I will read the theorem and I will do practice problem. So the diagonalization theorem, what does it tell me? Let A be an n by n matrix. A is diagonalizable. It means I can write it as a P times D times P inverse if and only if A has an linearly independent eigenvectors. So to be able to do it, as I mentioned a minute ago, I need this P to have the eigenvectors here has to be linearly independent. So the condition for a matrix to be diagonalizable is to have n linearly independent eigenvectors. And the question is, if I can find them, how the diagonalization would work. It means what's the P, what's the D. So the P is what is. So if V1 are those eigenvectors, those linearly independent eigenvectors, with corresponding eigenvalues, lambda 1 through lambda n, repeated according to their multiplicity. I will explain this in the examples. Then A can be written as P dP inverse. The columns of P will be those linearly independent eigenvectors. And the diagonal term of D would be the eigenvalue that correspond to eigenvectors. So the first column here will be the eigenvalue that correspond to V1. This will be the eigenvalue that correspond to V2, and so on and so forth. And we will we're going to be working with this diagonalization right now. So a matrix, we can diagonalize it, but to be able to do that, I need n linearly independent eigenvectors. So if A is a 2 by 2, to be able to diagonalize it, I need 2 linearly independent eigenvectors. It means intuitively I need a basis of eigenvectors. That's really the idea. To be able to factor it, I need a basis of eigenvectors. So if 3 by 3, I need 3 linearly. It means I need enough vectors to cover R3 or to be able to diagonalize the matrix. And that's really the idea. So let's do that. So we'll take now several matrices. So the theorem states that, so here I write it clearly, that a matrix is diagonalizable if we have enough eigenvectors to form a basis for Rn. That's really the idea. So I will work out 3 examples to totally clarify this idea. So example number 1, which is in your note, but we will work it out together. So I have the following matrix. And it's 1, 5, 2, 4. A simple matrix. And the question is diagonalize if possible. So if possible, it means I have to see if I have enough eigenvectors to cover the space R2 in this case. So to diagonalize, I need those linearly independent eigenvectors. So the only way to do it is to solve the whole eigenvalues, eigenvectors problem. So first I need to find the eigenvalues, and then I have to find the eigenvectors and see if I have 2 linearly independent ones. All right. Eigenvalues is not, by now we should kind of know it. We take the determinant of A lambda I and we set it equal to 0 and we solve for it. So I compute this one, minus 10, and 4 minus lambda. So if I do this, I distribute, I factor, and I will get this piece. Okay, so this is simple math. And this will give me 2 eigenvalues, lambda equal 1 minus 1, lambda equal to 6. But to diagonalize, I need 2 linearly independent eigenvectors. So let us go look for them. I have 2 eigenvalues. This one will give me a basis, and this will give me a basis. Let's look for all of them. So first, I need a basis for E minus 1. Means basically, it means I need all the vector x such that ax is minus 1 times x, because that's lambda x, which is, as we know, that's equivalent to solve a minus 1 times the identity x, minus 1 here because that's my lambda. It means a plus x equal to 0. That's what I need to solve. So I go back to my A. It's a 1 plus 1. That's a 2. That's a 2. That's a 5. I have to add 1. That's a 5. Remember that if you don't get free variable at this stage, you're doing something wrong. Because the determinant of this matrix, we chose the lambda. So the determinant of this matrix is 0. It means this matrix should not be invertible. It means this matrix, solving it should give me a infinitely many solution. So you get this stage, you don't get free variable, you're doing something wrong. It means if you only get the 0 solution, you're doing something wrong in the process. Now let us solve. Obviously, 5, 5, 2, 2, divide by 2 here, divide by 5, and do the echelon form. That's fairly simple. We should get this one. So here, obviously, this is my leading. It means my x2 is free, and my x1 is minus the x2. So every x that satisfies ax equal minus x, that's really what I'm solving for. So every x will have the following form. We put xt2 to be equal to t. It have to form a scalar times minus 1, 1. So a basis for E minus 1 will consist of the vector minus 1, 1. So now I have a lot of eigenvectors. I have a lot. Every scalar multiple of them, this is an eigenvector. Okay, but they are all linearly dependent on each other because they are all scalar multiple of minus 1, 1. But I have one at least, which is for the basis. Now my question is, do I have another eigenvector, which is linearly independent of that? I'll have to pick it up from lambda equal to 6. Because lambda equal minus 1 give me a lot, but they're all dependent on minus 1, 1. I need another one, which is linearly independent of minus 1, 1. So I have to go and I look for a basis for E6. So I have to look for each one of them. So again, mathematically, I am solving for the x's. So that when I take a times x, I get 6x. That's really what I am solving for. But solving this is hard. We solve the following. This is equivalent to solve this homogeneous system, which is much easier to solve. Now, very quickly, that's a homogeneous system. And my a is 1, so I have to take 6 from here and 6 from here. So take 6 from 1, which gives me a minus 5 and a 2 and a 5. And I have to take 6 from here, which is will give me a minus 2. As you realize, I'm having a free variable immediately. So we do that. That's, of course, is a 0. And this is minus 5, 2, and 0. I don't have no choice. So this will imply that x2 is free. What about x1? Now let us be careful. The first equation will read minus 5x1 plus 2x2 is equal to 0. It means x1 will be 2/5 x2. Okay. So every solution will be written. So every vector that satisfies this equation, I can write it as scalar times 2/5 and 1. So a basis for E6 would be the following vector. Something I mentioned before, you can use 2/5 1 as a basis or any scalar multiple of it, because E6, it means it's the following. Every scale, so if I draw, this is the vector 2/5 and this is the vector 1, that's E6. Every vector here has the property that if you pick any vector on this line, has the property that if you compute a times x will be somewhere here, 6 times it. Okay, so basis for E6 would be, instead of taking 2/5 and 1, I can take a scalar multiple of it. So I can take 2/5. Okay, just to make it easy. And now, do I have my 2 linearly independent eigenvectors? Minus 1, 1 is one eigenvector. 2, 5 is another eigenvector. So now I have 2 eigenvectors. I have a lot of eigenvectors, but I want 2 which are linearly independent. Do I have them? Minus 1, 1, 2, 5. Those are 2 eigenvectors. Are they linearly independent of each other? So since they are 2, it's easy. 2 vectors are linearly independent if they are not scalar multiple. And those 2 are obviously not scalar multiple of each other. So I have 2 linearly independent eigenvectors. It means this matrix is diagonalizable. So let's write this down. So I need them to be linearly independent. As I said, I have a lot, but I need 2 linearly independent. So A has 2 linearly independent eigenvectors. Okay, namely minus 1, 1 and 2, 5. Now you could have used 2/5 one, but I don't want to because it's easier not to work with fraction. So what does this mean? It means that my matrix A can be diagonalized. It means I can basically factor out A as a P times a D times P inverse. Another question is, what's the P and what's the D? All right, what is the P? The P is the matrix whose column are those eigenvectors. So that's -1 and 1. And the other column is the other eigenvector. That's the P. Now, what is the D? The D is the matrix whose term along the diagonal are the eigenvalue that correspond. So how do we write the D? We take, let's say I put -1, 1 as the first column. Right here, I need to write the eigenvalue that -1, 1 came from. Now, -1, 1, this was the eigenvector that corresponds to lambda equal -1. So right here will go the -1. That's how it works. To 5, this was the eigenvector that came from lambda equal to 6. So on the second column, I will have 0, 6. So that's what P is, and that's what D is. P inverse is just P inverse. P inverse is just the inverse of the matrix P. Now this is a 2 by 2, so finding the inverse of that is actually easy. So 1 over the determinant, which is -5, -2. So this is -1 over 7. And that's a 5, that's a -1, and -2, -1. So my matrix A now, I can write it in this, I can factor it out this way. 5 times -1, 0, 0, 6. So we can really break it apart and write as simple matrices. And this would be -5 over 7, 2 over 7, 1 over 7, and 1 over 7. So that's the factorization of the matrix A. That's how I can actually write it as product of things. Now, if I want A to the power, let's say A to the power 10. So how should I write this? So -1, 1, 2, 5, -5, 7. And now I need D to the 10. What's D to the 10? -1 to the 10, very easy. 0, 0, 6 to the power 10. And that's my diagonalization. Okay. Please ask questions as I move on. All right. So I will take 2 more examples because it's really, as you realize, it's not really hard. It's just the idea of checking those eigenvalues. So I will take 2 more examples before we finalize this section. All right. So example number 2 is the following. One, two, three, four. Okay. So example number 2, I will take the following matrix. I took a simple one because I didn't want the algebra to get in the way. 0, 1, 2. Okay, and the question is diagonalize if possible. We will have to do the exact same thing. First, we're going to find the eigenvalues. Are the eigenvalues easy or hard in this problem? Easy, absolutely. What are the eigenvalues? What's the determinant of A minus lambda R? It's 1 minus lambda times 2 minus lambda square. That's 0. It means I have lambda equal 1 and lambda equal to 2. This is the one I called algebraic multiplicity of 2. And that's algebraic multiplicity of 1. So very easy. And I did that because I don't want to compute a lot. Now for each one of them, I have to find the eigenspace. So I start for E1, basis for E1, lambda equal 1. So I need to solve the following simple system. AX, basically I'm solving this one. I'm looking for the vector that X actually, A doesn't really change. AX equal X, which is, as I said, equivalent to solve that's equal to 0. So we solve this very easily. I will have 1 minus 1, it's a 0, 0, 0. 0, 2 minus 1, it's a 1, and it's a 1, 0, 0, 1. Right? So, of course, we have to put it in an echelon form. Echelon form does not allow a row of 0 at the top, so I have to switch the whole picture around. I have to put it like 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 0. Too much zeros to make the problem easy. Leading. So this will give me x1 to be my free variable in this case. So here I will have x1 free, x3 0, and x2 is 0. So this will give me the following bases: 1, 0, 0. So basis for E1 is the vector 1, 0, 0. So I have one of them. To be diagonalizable, I need 3, but not only 3. I need 3 linearly independent ones. So I will go, I still have another eigenvalue to work with. So let us go after this one. So I will go after this one, lambda equal to 2. And basis for E2. So I need a basis for E2. So let me go back. So I have to find all the vector that XA stretches by 2. It means to get that, I need to solve the system. So I have to take 2 away. 1 minus 2 minus 1. 2 minus 2, that's a 0. 2 minus 2, it's a 0, 0, 0. Again, we have to solve this. I have a leading. There is nothing here. And I have a leading. So this will give me my x2 is free. I hope you guys start seeing the picture. My x3 is 0. And my x1 to be 0. So if every vector here will be a t, that's a t times 0, 1, 0. So a basis for E2 consists of the vector 0, 1, 0. So now there is no more eigenvalues. These are the only eigenvalues I have. So I have only 2 eigenvalues, 1 and 2. And I try to find a basis, E1, for the eigenvectors. E1 gave me 1 eigenvectors and bunch of others, which are scalar multiple of it. E2 gave me 1 eigenvectors and bunch of others, which are linearly dependent on that. So the question is, can I find 3 linearly independent eigenvectors for this matrix? Is this matrix diagonalizable? It means, does this matrix have 3? Absolutely not. There is no way I can have 3 linearly independent eigenvectors. I have this one and that one. Everything else, either a scalar multiple of this or a scalar multiple of that. So this matrix has only 2 linearly independent eigenvectors. 2 of them. So not there. There is no way we can factor out this matrix. So there is no way we can break it apart to make it into an easier matrix to work with. The problem of factorization is a problem of how can I make this matrix easy to work with. This matrix, as far as diagonalization is concerned, there is no way we can break it apart. There is something else we do with it, but we don't really go over it in this class here. Right? So this falls apart. So this matrix falls apart. Okay, any questions? Any questions? All right. If the number of eigenvalues doesn't match the number of columns, can you assume that the matrix is not diagonalizable? And the answer is no. Okay, and that's where my last questions is about. So what your classmate is asking, which is a very fair question, I have two eigenvalues here. So if I have only two eigenvalues, does this mean it's not going to be diagonalizable? I have this one and have this one of algebraic multiplicity 2. And the question, if this scenario occurs, does it mean it's not diagonalizable? And my answer is no, it can be diagonalizable because this one can give me sometimes two linearly independent eigenvectors. And that's what my last example is really bringing to the picture. So I gave two examples. In a scenario like this, it's not, but this doesn't mean that this is always the case. So the last example, I'll answer exactly Marcel's issue. And my last example is the following. Okay, so here's my last example. I have the following matrix. So A is the following matrix. It's minus 1, 3, 1, and 0, 0, 0. Why not? And 1 minus 3, 1, minus 3, minus 1. And the question is, again, diagonalize if possible. It means factor it out. Okay, that's really what they want. Factor it out. Okay, can I factor it out? So I really don't know unless I go through the whole process of finding eigenvalues and eigenvectors. So again, we have to start the eigenvalues. We compute the determinant of A minus lambda I. So I have to take away a lambda. Minus 1 minus lambda. 0, 1. 3, I have to take a lambda away. Minus 3. 1, 0, I have to take a lambda away. Okay, and now I have to do the compute the determinant. Of course, I have to do cofactor down this column. So I start with my checkerboard sign, plus, minus, plus, I don't care about this one. So this will give me minus lambda times, I get rid of those two, minus 1 minus lambda and a 1, 1 minus 1 minus lambda. So I have to go through the process. And this will give me minus lambda times the following. This times that will be 1 plus lambda squared, because I have the minus, times minus 1. So finally, this will give me, remember, we do not distribute because we want to solve. Solving is factoring, not the other way around. 1 plus lambda squared will give me lambda squared plus 2 lambda plus 1 minus 1. Now to solve, I have to factor. I think I can factor out the lambda again, and I will have equal to 0. So like in the previous problem, I have two eigenvalues. Lambda equal to 0. This algebraic multiplicity is 2. And lambda equal minus 2. All right, a comment on this side. Do we expect lambda equal to 0 to be an eigenvalue? Can anybody answer this question before I proceed? This matrix, do you think we should expect lambda equals 0 to be an eigenvalue? Yes. Can anybody give me a reason? Can we a little bit connect dots? So do we, before I go on, just to backtrack a little bit, do we expect this to be eigenvalue? Anybody can answer this question. Let me ask you one question. The matrix A, is it invertible? Yes or not? Can you just, by looking at it, decide if it's invertible or not? Is it invertible? I'm getting a lot of yeses. I want you to think about the question again. This matrix A, there's a whole column of 0. Can this matrix be invertible? No, absolutely not. Why it's not? Think about the determinant of this matrix. What's going to be the determinant of this matrix? If you do cofactor down this column, the determinant is going to be equal to 0. Immediately, absolutely not invertible. Even if you try to do all type of row operation you can, there is no way you can get a pivot in here. Regardless what you do, you will not have a pivot in here. So this matrix cannot also be reduced to the identity. So having this column here will make the matrix absolutely not invertible. Reduce it, there is no way you can create a pivot in here. You can never go to the identity because you have a bunch of 0. Regardless what you do, you can never touch this column. So whenever this matrix have a whole row of zeros, this matrix definitely not invertible. The matrix not invertible, the determinant of A equal to 0, it means AX equal 0 times X will have infinitely many solutions. Lambda equal to 0 is an eigenvalue. So this is just a comment on this side. Now let's go back to our problem. So lambda equal to 0 is an eigenvalue and lambda equal -2. Now to answer the question about diagonalization, I have to do the picture. So eigenvector. So for lambda equal to 0, I need to find the basis for E0. It means I need to find all the vector x such that AX equals 0 times x, because 0 is the eigenvalues. Basically, boils down to solve the homogeneous system, AX equal to 0. That means I have to solve A minus 0 times the identity, which is 0. It means I need to solve AX equal to 0. That's really what this boils down to. So now we take the matrix A, vector 0, and I plop it in here. -1, 3, 1, 1, -3, -1, and I solve. So we solve. Okay, something interesting here is happening. -1, 0, 1, 0. 3, multiply this by 3, -3 is 0, 0, 0. -1 plus 1 is 0, 0, and 0. So I'm getting that. Okay. So how many free variables I have? How many free variables I have? That's my only leading. What does it mean? This is free variable, and this is a free variable. So x2 is free, and x3 is free. And x1 is what? The first row read minus x1 plus x3 equal to 0. It means x1 is minus x3. It means x1 is equal to x3. So I actually had two free variables in this particular scenario. So I can put this to be S and this to be T. And then when I will try to write it in vector form, then I'm going to have the following. So every vector now will be written. So every vector satisfies AX equal to 0. So I'm really after the null of A in this case. I will write it as this way. So the first one will be, since x1 is x3, and this will be 0, 1, 0. T will be 1, 0, and 1. So a basis for E0 will consist now of 2 vectors. And this will help Marcel kind of visualize what's really going on in this scenario. So lambda equal to 0 gave rise to 2 linearly independent eigenvectors. Those are obviously linearly independent. There is no way you can scale this one to get here. Those are 2 vectors. But we need 3 and linearly independent. But I still have one that I haven't really worked with. So I still have lambda equal, the other eigenvalue was lambda equal minus 2. And I need to go after the eigenvectors that correspond to that. So I will solve AX equal minus 2 times X. It means A plus 2IX equal to 0. So be very careful when you have a negative one. When you bring it to the other side, it's going to become positive. So I will do that. So I have A right here. And then I just add. So the original matrix is minus 1 plus 2. That's give me a 1, 0, and a 1. So I'm going back to my original matrix, which is right there. And 3, I have to have a 2 in here. And a minus 3. And finally 1 and a 0. And I have to add minus 1 plus 2. It's a 1. And I solve. I have to have 3 variables, as I said, otherwise what I'm doing is not really working, and this will bring up the following. So we do all the math that we usually do, and I will get the following matrix. I will get 1, 0, 1. The last row is obviously a 0 because minus 1, and this minus 3 plus 3, it's a 0. That's a 2, and that will give me minus 3. Minus 3 minus 3 is going to give me a minus 6 and a 0. So I solve the regular way. Now I have only, so that's a leading. I only have 1 free variable, and if we solve for it, we realize that it will be, that's a 1, and that will be 2 equal to 6, which will give me a 3 right here, and the first one will give me a minus 1. So a basis for E minus 2 will be the vector minus 1, 3, and 2. So now let us see what we got here. What we got here is the following. The eigenvalue lambda equals 0 gave me 2 linearly independent eigenvectors. The eigenvalue lambda equal minus 2 gave me this eigenvector. So now the question now, and every other eigenvectors is either a linear combination of those 2 or scalar multiple of this vector. But I have 3. So now I have 3 eigenvectors. 0, 1, 0, and 1, 0, 1, and minus 1, 3, 1. Those are the eigenvectors that correspond to lambda equals 0, and this one corresponds to lambda equal minus 2. So those are 3 of them. So the question is that, are they linearly independent? And the question is they are. You can check it. And usually there is a theorem that guarantees that the eigenvectors that correspond to those different eigenvalues, when you put them together, will always be linearly independent. But those are linearly independent. Check. It means take their matrices and show that they are linearly independent. So now my matrix A is a 3 by 3. It has 3 linearly independent eigenvectors. Means basically, intuitively, it needs you need a basis for R3 that the terms of the basis are eigenvectors. So I have 3 linearly independent eigenvectors. independent, it means that my matrix A is immediately diagonalizable. Okay, so even if I had two eigenvalues, and I can still diagonalize. So what's really gonna be the picture here is lambda equal to 0 was of algebraic multiplicity 2. But the eigenspace that correspond to it gave me two eigenvalues, that gave me two eigenvectors. In the previous case, lambda equal to 2 was algebraic multiplicity 2, but its eigenspace gave me only one eigenvector, one vector in the basis. So this was not diagonalizable, but this will be diagonalizable because it gives me the two that I will need. So my matrix is diagonalizable, and then my last step is, okay, let's go ahead and diagonalize it. So how do we diagonalize? It means what's the P and what's the D. So what's the P in here? The P is the matrix whose column are the eigenvectors. So 0, 1, 0, 1, 0, 1, minus 3, 1. D is the matrix whose column are the eigenvalues, the diagonal one. How we pick the eigenvalues? Okay, we said that. We start with this. And we write the eigenvalue that correspond to it. So if this is 0, 1, 0, the eigenvalue that this one came from was 0. 1, 0, 1. Which eigenvalue this one came from? 0. Minus 1, 3. This eigenvalue came from where? 0, 0, minus 2. Okay? This is diagonal because the terms of the diagonal are 0. I don't care about what's on the diagonal. There could be zeros or not 0. It doesn't really matter. So my matrix A now could be totally factored this way. So that's an easier way of representing the matrix. One last comment before I about P is, let us say a student did not use this order. So the order, like I picked 0, 1, 0, 1, 0, 1, minus 1, 3. Suppose a student picked minus 1, 3, 1, 0, 1, 1, let us say 1, 0, 1. So pick the different order for the eigenvectors. You can do that. There is no problem. But what change will be the D. Because if you change the order, so change order of those, will change the D. Because the way the D work is, if the first column is minus 1, 3, the first one here should be the eigenvalue that correspond to that. Then this will be minus 2, 0, 0. That's how it will work. Now, this one, it's 0, 0, 0, and this one will be 0, 0, 0. Okay, Danielle, I did not understand your question. Voilà. Okay, so this will be the diagonal. So you can change the order of the vectors. It doesn't really matter, but when you change them, you have to change the order of the eigenvalues. So they have to correspond to each other. That's how it works. Now I finished the diagonalization with actually, so matrices can or cannot be diagonalizable. A lot of them will be diagonalizable, but not all of them. There are a lot that we cannot diagonalize, but there is, as I said, a different factorization for those matrices that is a little bit at the end of the book. We don't really reach that much. That I finished with two theorems. The first theorem tells me the following. The proof is hard, so I totally skipped the proof. But the theorem tells me the following, and I'll explain it in words. It said that if A is an n by n matrix, so a bunch of matrix, and V1 through Vk are eigenvectors that correspond to different eigenvalues. Lambda, it means, what do I mean by distinct? The word distinct have to be understood. The word distinct, it means they are not the same. So V1 is an eigenvectors, eigenvalues lambda 1, V2 lambda 2, but all those are different numbers. Then automatically they are linearly independent, the eigenvectors. It means, let's say I have a matrix A, And this matrix have one eigenvalue lambda equal 2. It has an eigenvalue lambda equal to 3, distinct. So I find an eigenvectors for this. I find an eigen, and suppose that another one, lambda equal to 4. Immediately those will be linearly independent. That's what the theorem says. And this leads to the following thing, that following special type of matrices which are always diagonalizable. So the theorem would lead to a case where diagonalization is automatic. When is diagonalization automatic? If the matrix has n distinct eigenvalues. It means you have a matrix, you find the eigenvalues, they are all different. None of them repeat. So all of them are of algebraic multiplicity 1. None of them repeat. It means immediately it's diagonalizable. So if they don't repeat, it's immediately diagonalizable. So for example, if I take this matrix, I took a diagonal, the eigenvalues in this particular scenario will be 2, 5, minus 1. This matrix will be immediately diagonalizable because what's happened when I find the eigenvectors for this one, that one, they will be automatically linearly independent. But whenever the matrix have repeated eigenvalues, and then we actually don't know, we have to go and find the eigenvector that corresponds to it to realize whether it's diagonalizable or not. Okay, so that's the idea of diagonalization. The last idea I would like to talk about in this class is, which is not in my note, but I will put it out, is back to eigenvalues. All the eigenvalues, remember, eigenvalues, to find them, we need to solve a determinant. Means we need to solve a polynomial. And this polynomial is, if I have a 2 by 2 matrix, it's a polynomial of degree 2, 3 by 3, polynomial of degree 3. But as we know that sometimes a polynomial does not have a real solution. It means you solve it, you don't have real solution. But you can have complex values. So eigenvalues can be complex numbers. And I will a little bit talk about that because we have to be aware of it. So complex eigenvalues. And I promise I will put those notes on Blackboard. Okay. So before I talk about complex eigenvalues, I actually don't know how much you guys know about complex numbers. Are you familiar a little bit with them? On chat, tell me, do you know a little bit about complex numbers? Very good. So I don't need a lot. Actually, I really need a minimum. So what is a complex number? A complex number is a number of the form, basically a plus b I. That's a complex number. Okay, tiny bit. I don't need more than that. So where a and b are real numbers, and I is this imaginary number that has the property that I squared is minus 1. This is imaginary number that have this property. That's about what I actually need in a way. So a typical complex number, 2 plus 3i, whatever, 5 minus 2i. So the real part is 2, that's the a. The imaginary part is 3. Here, the real part is 5. The imaginary part is minus 2. So these are the complex numbers. Now, we usually use R to denote all the real numbers. Complex number, because it's a C, we use the letter C. So C would denote all the collection or the set of all complex numbers. What does it mean? It means all numbers of the form a plus bi, a and b real. So C is all of them, not 1, not 2. Is like R represent all real number. We use the letter C, and sometimes you will have a bar in it, not all the time. It denotes all possible complex numbers. So in particular, real numbers are themselves complex numbers where the imaginary part, this is equal to 0. So the real numbers are complex in this particular case. And usually we represent complex numbers on a plane like this. So if you have the point 2 plus 3i, we represent it by, this is 2 and this is 3, and we represent it as a point in the plane. Okay. Now another thing, and then we will take care of complex eigenvalues. Let us remember what R2 is. R2 was nothing more than all ordered pair of numbers, x, y. X, y are real number. That's where R coming from. So what does C2 represent? Okay, so it's a bit abstract, but actually the same idea. It's ordered pair of stuff. Also the set of all ordered pairs. But ordered pairs of what? Ordered pairs where the entries are complex numbers. So C2, it means all ordered pairs ZW where Z and W are complex numbers. And those are called vectors. The same way we call those vectors, we actually call those vectors where entries are complex. So example, a typical vector in C2, that's a typical vector in C2. It's a vector where the entries are complex. Okay, so we can do all type of vectors. Whatever I can put to I, for example. So these are vectors in C2 means ordered pair, or each entry by itself is a complex number. Now, let's see where complex eigenvectors eigenvalues comes up. Remember, what's an eigenvalue? If you have a matrix A, an eigenvalue is a number x, or sorry, an eigenvectors is a vector x such that the way A acts on it is to stretch it. That's really what it is. This is x, and this is ax equal lambda x. Now suppose I take the following matrix. I take the matrix that does the following. That takes a vector x and rotate by, let us say, 90 degrees or pi over 2. But I think about this matrix. So what it does, takes a vector and it rotated by 90 degrees. And we know basically this matrix. What is this matrix? That's a rotation by 90 degrees. It's cosine of 90. Now cosine of 90, that's a 0. Sine of 90, it's a 1. Minus the sine of 90, that's the matrix A. And the effect of this is to rotate. Now question probably is a little bit hard. So that's what it does to x. It takes it here, it rotated. So the question, is there intuitively a vector x for this particular matrix? Is it possible to find a vector that A stretch by a scalar? Absolutely not. It can't, because what x does is actually rotate. So there is no way you can find a vector that x will stretch. So our intuition tells us that, you know, there are no eigenvectors. And the truth is that there are, but those eigenvectors will have complex entries, not real entries anymore. So I'm going to take this problem and I will work it out slowly. So I'm going to take the following matrix, the one I'm talking about, A, which is 0, 1, minus 1, 0. And I will find the question number 1, find the eigenvalues. So the eigenvalues. So I need to set the determinant of A minus lambda I equal to 0 and proceed. So let us compute the determinant. So I have to take, that's a minus lambda, that's a 1, minus 1, minus lambda. So this would be equal lambda square minus minus plus lambda. And now you start seeing what's really happening. I will put this equal to 0. I need to solve. Now, it means lambda squared is minus 1, minus 1. It means that the solution consists of complex numbers at this stage. Lambda is plus or minus I. So now my eigenvalues are complex number, not real numbers anymore. Okay, so that's the first issue. That's why we want to be able to see what's happening. Now what about the eigenvectors? I will do one, and then I will let you work with the other. Now find the eigenvectors. So we will not let our basis for the eigen. So find the eigenvectors. We're not letting I get in the way. We will treat it as a constant I. So first, for lambda equal I. So we will find all the vectors. So that's what I will be doing. Find all the vector x such that is I times x. That's what I will find. It means x will multiply them by I. It means I need to solve A minus I times the identity x equal to 0. So I will take my matrix, and this time I have to take minus I. So the 0, it's minus I, minus 1, 1 minus I. So I will show you in a second. So I took I from every term, and now I need to solve. As I said, do not let I get in the way. We solve in the regular way we've been solving. No more, no less. Okay, so we go to the echelon form, and then we solve. So if you were doing this yourself, how would you start? What would you do? Please, we're almost done. What would you do if you were doing this yourself? Don't let I, as I said, get in the way. Okay, if I am doing it, I like to have my 1 in here. I is a constant. I'm not really bothered about it. 1 minus I minus I minus 1. Solve as if it's a constant. Now I need to create a 0 in here.
So just multiply the first row by I. Yeah.
Exactly. Multiply the first row by I. It's verbatim the same. Thanks. So you multiply the first row by I, add it to the second, and this will be the second. This will have to give us free variable. If you don't get free variable, again, we're doing something wrong because the theory actually generalizes. The complex numbers will not give us an issue. 0. I minus I is a 0. Now I multiplied by minus I, so here I times minus I. I times I is I squared, that's a negative. Negative times negative will give me a positive. So when I multiply this one by minus I, this gives me a 1. 1 minus 1 will give me a 0. So now I solve it exactly the same way. So even if I have those complex entries, I really solve it the same way as I solve for the real numbers. It's just harder. Nothing more than that. So now I will have x2 will be a free variable. And x1, that's what's going to happen. If I solve this, that's read x1 minus I x2 equal to 0. It means x1 is I x2. So the eigenvalues will be all the vectors of the form a scalar times I and 1. So eigenvectors will be all vectors of the form t times I1, where t is any scalar. So the typical eigenvectors is the vector I1 in this case. And we can diagonalize those matrices. So if I go for lambda equal minus I will be able to find actually another one and another eigenvalues, and I can even diagonalize this matrix. But the idea here is actually to learn how we do that if we have complex eigenvectors, eigenvalues, and the problem is exactly the same, and we can pull up all the eigenvectors that we need. Okay, so you will definitely, I will assign problem along those lines for next time, so you guys practice those ideas. So that's it for today. 2 things. Your exam review will be down. Your exam is a week from Thursday, so which will put us May 7th. So that's when your exam will be. It will be, of course, cumulative. It means you're responsible for everything we've covered, which is by now, we repeat the idea so often that nothing should be forgotten, I hope. I will put the review in the following way. I will put everything you're responsible for. It means all the ideas. I do not give you a review in terms, I will not give you last year's final. I usually don't do that on the final, but you will have exam 1 to work with, exam 2 to work with. You will have last year's exam 1, last year exam 2 to work with, to review. And the new material will be definitely quite present. So the new material that you're responsible for and you're being quizzed over it will be determinant, will be quite represented on your exam. Eigenvectors, eigenvalue will be quite represented. Diagonalization will be quite represented, and complex eigenvalue. So those will be quite represented. Unfortunately, the exams start at 8 o'clock in the morning. And I will post a review, yes. How much time do we have for the final? You will have 2 hours, and that's for 2 hours to take the final. Is there going to be a quiz on Thursday? And the answer is absolutely yes. There will be a quiz on Thursday. Sorry, Daniel, I don't change. Any other questions? Okay, now the last thing I would like to ask you, please fill out the evaluation. I know that some did, but not a lot did not. Please do fill out the evaluation. They are important for us. Okay, where is the evaluation at? You should receive emails, lots of them. My understanding, not on Blackboard, you guys should be receiving emails from PNW, right? Anybody else? Yes, you guys should be receiving emails, and you should fill out this evaluation, and that will be very much appreciated. Okay, any other question before I let you go? All right, enjoy the rest of the day. Bye, guys.